Hello students, this is Mr. Ezra. Today we are going to actually graph some rational functions. So up until this point we have found lots of different types of asymptotes from vertical to horizontal to slant. We've talked about how to find holes on the graph and some other characteristics. And today we're actually going to learn how to graph them. I'll go ahead and say that having your graphing calculator will help you out a whole bunch on this. So get that joker out and have it with you. And as we're practicing today, kind of practice putting in the functions, make sure you're getting what I'm getting and that it's all working out for you. How to graph these rational functions is pretty simple. First, start by getting your asymptotes and holes on the graph. They provide guidelines for you so that you know what your function should look like. And also, they are not necessarily going to show up on the graph, but they are important. So I want to see those on there as dashed lines and as circles. After that, we're going to get our calculator out, go to y equals and enter the function in there, and then go to the table and get a bunch of ordered pairs. And I'll kind of show you how to use all those functions in the calculator as we look at some problems together. So example 1, we've got 3x minus 4 over x minus 2 that we want to get on the graph. So I get out my graphing calculator. I'm going to go to y equals. And you will notice that when I put this in the calculator, I want to make sure that I put the top part in parentheses and the bottom part in parentheses, because what happens with your calculator if you don't do that is it doesn't understand what it's supposed to do in what order, and you want to group the numerator and the denominator together. So I've got 3x minus 4 in parentheses divided by x minus 2, which is this rational function right here. Now, I would like to look at the graph of this and see what it looks like. So I'm going to go to Zoom, and I'm going to choose Zoom Standard. Zoom Standard goes from -10 to +10 on the x and y axis, so number 6, Zoom Standard is a good choice for us. Now, your calculator may or may not have this line down through, let's see, that's through 2 on the x-axis. Mine does. It really depends on which version of the calculator you have and what operating system you have on there. Sometimes it has trouble with asymptotes. It doesn't really do a good job always of differentiating what's an asymptote and what's part of the function. That's your job. So what you want to notice is these straight down lines are usually going to be asymptotes. They're not going to be part of the function themselves, but they're where the function cannot exist. And everything else looks like it follows our graph pretty good. We're coming down and then over. Now, I want actual ordered pairs. I don't want to just sketch this out. I want to know exactly where it's happening. So I go to my table by hitting second graph, and I get a list of ordered pairs that I can scroll through. Now notice this error here after 2. An input of 2, an x value of 2 gives you an error in your calculator. Why? We already know why. There's a vertical asymptote through an x value of 2. So the function can't exist there, and a calculator realizes that, and it says error. Now, you don't have to graph every ordered pair, right? We can start at -10, comma 2.8, which is left 10 up almost to 3. And then maybe go to -8, 2.8. And I'll go ahead and put a bunch of these other dots in, kind of curving in towards the asymptote. Now, as I approach the asymptote, I'm going to include more detail as it kind of starts to turn the corner here. So I've already got 0, 2. I'm going to put in 1, 1. And I already have an error right there. So what's happening is this function is hugging this asymptote, coming down, and then it's going to hug this asymptote. And to get that graphed, I do my best at sketching through all of these points. And I just want to make sure that this function is kind of approaching that asymptote the best that I can do. So I do want it to get closer and closer and closer, but I don't want it to go through that asymptote because that's not possible. So I've got my arrows on the end. That's part of my function. The other half is going to be on the other side of the asymptote. So I've got 3, 5, 4, 4. 3, 5 is right here. 4, 4. Get a few more, maybe 6, 3.5. And 10, 3.25. So all the way over here at 10, 3.25. So what's happening is I'm hugging this asymptote. I start to curve through here, and then I hug the other asymptote. I just want to kind of carefully come down away from that asymptote, go through these points, and then go towards the other asymptote. Now remember, vertical asymptotes cannot be crossed, ever. It's not possible. The function doesn't exist there. Horizontal asymptotes probably are not going to be crossed very often, but they are more of a suggestion, and occasionally your function will go through that asymptote, and if it does, it shouldn't go very far from it. Like if it goes through, it should still kind of hug close to it and stay close to it um, throughout the function. It does happen sometimes. So verticals cannot be crossed. Horizontals, if it does, it should stay kind of close to it. Now, what do you do if you don't have a graphing calculator, if you can't get to that table of values? Well, you just have to choose a whole bunch of x values, and this wouldn't even be enough, but I'd have to get a whole bunch of x values. I'd have to plug them in for x to get all the y's that go with it. And it's okay. You can do it that way. It's just going to take you a lot more time. So the graphing calculator is going to find all of those ordered pairs for you rather than you plugging in the x values and then finding the y values to get your ordered pair. I prefer to use my technology since I've got it rather than to spend a whole bunch of time doing calculations that I'm going to use a calculator probably to do anyway, or I'm going to do it in my head. And it's not really testing whether I know how to graph this function. So I encourage you to use your graphing calculators for this. Now we've still got some stuff over here that we will answer a little bit later. Today we're just going to focus on graphs. So let's look at another example. All right, in example 2, when I do this, I don't generally put in the reduced or factored graph. I start with the original function. So when I go back to y equals for this one, I'm going to plug in 2 divided by, actually I should clear this out, and then do 2 divided by x squared minus 4. Now remember, parentheses help your calculator to know that the x squared minus 4 goes together. Technically on this one I wouldn't have to put it on the 2, but I did anyway just so that it's consistent with everything else that I'm doing. And then I always like to stop off at the graph. And you see how the graph has trouble with those asymptotes. There's 2 of them here. It has a lot of trouble with that. That's okay. Okay, but so this graph is not going to be exactly what it looks like. Instead, we're going to have to go to the table to get those ordered pair. Now, I'm just going to do this really quickly, and then I'll be back in a second. I would encourage that you're doing this on your own, that you're plugging these into your function. I'm sorry, that you are plugging this function into your y equals, and then getting the order pairs, putting it on the graph, and then checking to see if you get it right. All right, so I've gone through and graphed all of those points, and as I graphed them, I noticed that the general pattern was that it was really hugging tight to this asymptote, turning a corner right here and really hugging tight to that one. Same thing down here, we're really close to this asymptote, we curve up here and then back down, and then over here it hugs close. All right, so that's graph number 2 out of the way. Let's go to graph 3. Again, when I go to y equals, I'm going to clear it out and I'll put the original function in there. All right, I can see that this pattern seems to fit my graph pretty good. So now I'll go to the table to get those ordered pairs going all the way back up to -10. And then I'll just graph as many of them as I can. Now remember, I'm estimating where 0.67 is. I know that I'm going to go left 10 and up a little bit more than halfway. So I'm putting a dot here, but I'm just estimating where it is. All right, so this is our first example of a function where we cross an asymptote. Okay, so you'll notice over here it seemed to really hug this asymptote on this horizontal asymptote, go down and hug the vertical. We have function coming down from the top in between and going through these points and going up. And on the right side of the right asymptote, the right vertical asymptote, we begin to just very slightly cross over the horizontal asymptote. This was like 1.06 and 1.09. I'm really close to it, and it just hugs along it and goes along it. And remember, I said that is okay. It's a suggestion. It happens sometimes with horizontal asymptotes. Remember, all I'm doing is going to y equals, clearing out what's there, and putting the new function in using parentheses. And that's it. Once I do that, I go to the table to get a list of ordered pair, and you can graph that function. All right, so this function here When I looked at the graph, the asymptote was there, and we don't see much of it. When I went to the table, I was able to get a handful of ordered pairs. I already had the intercepts graphed, so you don't really see it hugging the asymptotes as much because of, I guess, how zoomed in it is compared to the function. But we do see a curve up here and a curve down here, and if you get those, you should be doing pretty good. All right, so this function is close to the asymptote, turns up about right here, and remember it's going to hug that asymptote. It never will cross a vertical asymptote. It comes up from the vertical asymptote, curves in right here, and goes back down. And then this one over here is going to hug the asymptote, start to curve towards the other one. No asymptotes are crossed here at all. No horizontal asymptotes. So we kind of looks like a frowny face to me. All right, so it looks like this function is hugging the asymptote. So you see why it's nice to have these asymptotes graphed first, because they let you know that the kind of some guidelines for places where your function should not go. And that's nice to know. It also gives you an idea of when you've done something wrong. So if your graph doesn't match the asymptotes that you drew, either you made a mistake entering it into your calculator or you made a mistake when you were identifying the asymptote. I want to point out before we go to the points that the graphing calculator does not always do a good job of showing holes. So we see the function just kind of goes through that hole. We don't see it on the graphing calculator. So it's important to be able to identify holes and put them on as an open circle and then go to your table. You will notice that for most of you, that your calculator will still give you an error at an x value of -2, showing that the function is not defined there, which means it's a circle. I'm sorry, that it's a hole or an asymptote, but in this case, a hole. All right, so as we're graphing this, we want to head towards the hole. Stop drawing our function at the hole so that that hole is still there. You know, make sure that you can see the hole, and then we'll start at the hole. So there should be that circle right there at the function. I'm sorry, there should be that circle right there where the hole is supposed to be, and you want to keep it there. You don't want to let your function cross through it because technically the function does not exist at that spot. And you just connect the dots, follow through the curves, and you've got it graphed. So we've got our graph. There is a hole right here. So we want to make sure that open circle is there so that we can see that there's a hole there. We've hugged our asymptotes, given them a nice good squeeze, and things are looking well. So all right, so you can see this function. We already graphed it on the graph. You can see it is linear because it reduces to a linear function of x plus 3, which means it goes through the y-axis at 3 and it has a slope of up 1 over 1. But I do want to remind you that there was a hole right here that we identified when we were finding holes earlier. That hole doesn't necessarily show up on this graph, but when you go to the table and you start graphing all these points, if that's the method that you use rather than using slope-intercept, you do see 5 error, which indicates that there's something going on there. In this case, it's a hole. Well, friends, that is it for today. We spent a lot of examples today just looking at how to do the same thing over and over again. Put that function in y equals, use that your graphing calculator to get a list of ordered pairs of xy pairs, and then get those xy pairs onto your graph and make sure that it matches the asymptotes and holes that you've already drawn. I hope that you are successful with this. I hope at this point this is pretty easy for you, but if you run into any questions, please let me know.